The Void of Space. Hello and welcome to the second episode of ScienceTime, the podcast series where we take a look at peculiar scientific topics and try to understand them. I'm your host, Corbin, and today we're going to be talking about black holes. In the last episode, we got into a bit on how powerful they were, but we never really got deep into what they were. Let's start off with a loaded question. What is a black hole? A black hole is a very massive quote-unquote object, and I use quotes here because I'd argue that it isn't really an object, but rather a lack of matter. But the formal definition for a black hole is, quote, a black hole is a place in space where gravity pulls so much that even light cannot get out. The gravity is so strong because the matter has been squeezed into a tiny space, unquote. Now you might notice that the definition is a little vague here. Matter squeezed into a tiny space doesn't sound all that specific. If that's the case, then why aren't black holes formed every time someone uses a hydraulic press? Well, it's because of the scale of the size that we're talking about. If you crush an empty soda can under your foot, the amount of mass in the soda can hasn't changed, but its area has. For example, if you wanted to make the Earth a black hole, you'd need to make the radius of Earth about 8.7 millimeters. This equates to a volume of 2,758 millimeters cubed, and this is about 6.6 times 10 to the negative 15th times smaller, or a 6.6 with 15 zeros behind it. And if you want to make the black hole out of a soda can, using the equation to find the volume of it, which would be 4,048 millimeters cubed, and using the difference in volume between the black hole Earth and normal Earth, we get the size of the Coke can, which would be 2.7 times 10 to the negative 12th millimeters cubed. Now, for comparison, the average volume of an atom is 0.5 nanometers. The volume for this Coke can would be 2.7 times 10 to the negative 6 nanometers, which is considerably smaller than a quark, the smallest thing inside of this universe. Now, who came up with the term black hole, and how was it discovered? An American astronomer named John Wheeler coined the term black hole in 1967, but black holes were theorized back in 1783, when a British scientist named John Mitchell actually had a great observation that massive objects trapped light to the point where it could not escape. A famous name actually came up with the formal idea of a black hole in 1916, however. This was Albert Einstein, a name who I'm sure doesn't need any introduction. Albert Einstein's theory of general relativity states that matter could be packed into infinitely warped regions of space surrounded by boundaries called the event horizons, from which within nothing can escape. Then came the Schwarzschild solution, which revolutionized the idea of a black hole. Essentially, in 1916, a German astronomer named Karl Schwarzschild solved Einstein's mathematical equations for a black hole, and came up with a model describing a black hole's gravitational pull. Then, in 1939, J. Robert Oppenheimer and Hartland Snyder came up with the theory that black holes could form by a star dying. Instead of creating a supernova, these stars could collapse in on themselves due to the immense gravity, creating a void of itself. Hawking radiation was the next significant thing, stating that a black hole would eventually explode and deteriorate over time due to them emitting small particles known as Hawking radiation. Then came the first picture of a black hole. This massive beast came from the galaxy M87, and it revolutionized our ideas. So, in sci-fi movies, or any other media that you might consume, you might have heard the term, quote, this black hole breaks the space-time continuum, unquote, or something to that effect. But what is the space-time continuum anyways? The space-time continuum is a theory that space and time, by themselves, will fade away if not interacting with each other. They're the fabric of our reality, and in order for them to be stable, they need to be intertwined. So, with this, how does a black hole quote-unquote bend space-time? Well, for this we need to go back to general relativity. The full theory is very complex, so we won't touch it all, but in his theory, everything that has mass quote-unquote bends the space-time continuum. For example, imagine making a straight line on a balloon. That is space-time. Now imagine you have a massive object, and the more massive the object is, the more the balloon is blown up. Eventually, the line of the balloon will be curved even though you drew it to be straight. Essentially, space and time are one straight line. However, with massive objects, space-time can become bent, giving it strange properties. For example, let's look at light's properties. Light moves at a constant speed of 3 times 10 to the 8th meters per second, and this speed cannot change inside of a vacuum. Let's look at the sun. It's a massive object that distorts space around it. This means that in order for light to travel around it, it has to go further than if it was going in a straight line. Now, since the speed of light can't change, what can? Time. Time dilation happens here, and is basically how time travel is possible. What basically happens is the time for the light to travel the further distance feels different. A good example of this is if you were going the speed of light and 1 second passed for you, a longer amount of time would have passed on Earth due to your speed. Unfortunately, or rather maybe fortunately, the massiveness between us and the sun is astronomical, so we affect space-time very differently and perceive it very differently. Now, let's understand how scientists even found black holes. If everything disappears inside of them, it should be impossible, right? Well, let's use a real-life example here. Let's say you jump and you don't float off into space. That means that there's a force acting upon you, but you don't know where it's coming from. One day you do an experiment where you drop things from different heights. All of them fall down to the ground, and from this you can conclude that there's a force acting upon every object around you. Since they all fall to the ground, you can conclude that either 1, the ground has a mysterious force and this force keeps the planet together, meaning that the source should be identifiable if we can calculate the radius of the planet, assuming that it's inside of it, because everything doesn't fly off into space, or 2, everything wants to stay still, and in order to do this, it needs to be on a stable surface. Either way, you'd be right because things have inertia, but conclusion 1 is how scientists found black holes. They observed stars and other massive objects being pulled from their orbits at different speeds, and from there, once they had observed the fastest object being pulled from orbit into one specific place, they understood that there was, in fact, a black hole there. Now, we'll be getting into what it would be like to be eaten by a black hole. No one wants to get eaten by a black hole. That sounds awful, but I'm sure some of you guys are at least a bit morbidly curious by the thought of what it would be like. Well, first things first. You would start to accelerate very, very fast. It'd be like falling off the Eiffel Tower, except you keep on speeding up because there's no terminal velocity due to the lack of an atmosphere. You would simply approach the speed of light the further you fall, and there is no getting back. Once you're in the event horizon, from there your body would try and turn into a noodle. What would happen is you would stretch out vertically and become thinner horizontally. This is because of all the forces acting upon your body, and you would also experience extreme time dilation as you are around a massive object that bends space-time. You're now going the speed of light, or at least close to it, and because of general relativity, we know that the faster you're going to compared to the speed of light, the more time dilation you're experiencing. This means that you would see everything that had fallen inside the black hole, and everything that will fall inside the black hole. This is a quite morbid way to end an episode, but that's all for this week. Tune into next week's podcast for an exploration of time travel. This has been Science Time. Thank you all for listening in. Have a wonderful week.